Me. It's nice to be here electronically, and I'm excited to come spend some time in Paris in a couple months. So this is work that we've done recently on using machine learning on acoustic emission spectra in ceramic matrix composites in order to identify the damage mechanism that caused it. So I'm going to talk about these ceramic matrix composites, or CMCs, and what they are is it's basically like a ceramic fiber. It's a silicon carbide fiber inside a silicon carbide matrix with a weak fiber matrix interface, like a boron nitride. They're of interest for a lot of different high temperature applications, especially in the aerospace field and space field. It's been really tough to use acoustic emission for everything that could be used for. Like, acoustic emission has a wealth of information in it, and it's been a long-standing question if you can even identify damage mechanisms inside of CMCs. Part of that stems from the fact that their constituents are elastically similar. The fiber is the same material as the matrix, and so that makes it really hard, but it would be incredibly useful to be able to do this. And so that's what we've been working on. This is work that my graduate student, Kaylin Muir, has done. And this is in collaboration with NASA, University of Michigan, and two other people at UCSB. I'll go forward from there. So these CMCs, are these ceramic matrix composites, as you can see from the Ashby plot on the right, are exceptionally useful for lightweighting and for using them in extreme environment applications, high stress, high temperature, radiation. And so they're of exceptional value in the aerospace and space fields because of their ability to withstand high temperatures, withstand corrosion, which will increase fuel efficiency, increase payload capacity. But some of the problems that we're running into with these is that we don't have a good understanding of what happens to damage inside the material. There's been a lot of work on actually using acoustic emission to look at bulk damage, but it can only identify where the damage is and kind of its propagation. You can backtrack where it was, but you don't know what it was. And in order to both structurally health monitor these composites, a matrix crack is a lot different than a fiber break. And if you start seeing a lot of fiber breaks, that means you're nearing some sort of catastrophic failure. So it'd be incredibly useful to be able to know what damage mechanism was causing that signal. And then also not just structural health monitoring, but to model these materials for reliability, to tailor them for reliability, to model them for life assessment. We need to know how the damage is progressing and what mechanisms are happening based on, layup, based on geometry, based on thermomechanical loading conditions, so that we can model complex parts, so that we can understand complex parts. And right now we're not able to do that because we simply don't have enough information. So the way that they're constructed, they are this composite material, and you have this reinforcing ceramic phase, these ceramic fibers, which you can see in this image, this micrograph, coupled to a ceramic matrix with a weak boron nitride interface. The actual composites that are used in testing and in service look pretty ugly. So this is the example of the one that we're working with now, and you'll see a lot of pores. This is typical for a CMC in some ways. This is what's called a mini composite. Its fibers just aligned vertically with a matrix, and so we can pull them, have a limited set of deformation mechanisms that we can then validate. So we're starting with this question of, can we even identify damage mechanisms? And so we're starting with this unidirectional mini composite to try to answer that. The reason that CMCs have so much damage tolerance, or better damage tolerance than a ceramic, is because in a monolithic ceramic, you would start a crack and you would just propagate it through the entire ceramic. But in a composite, you have fiber bridging, you have crack deflection, you have all these things that kind of bypass, this interface effects that bypass the natural toughness of a monolithic ceramic. But these these mechanisms and this complex layup complicate lifetime prediction, and it really limits its application space, our inability to model these materials. So even in a very simple composite geometry like a mini composite, you have a number of deformation mechanisms active. You have matrix cracking, which pops in at low stress. So it's almost like popcorn. These effects are happening like boom, 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 boom. And so you start to hear when you put these acoustic emission sensors on, which is just listening, right? So acoustic emission, anything, when it breaks, it makes a noise. You break a piece of clay, you'll hear the noise. This is the same idea, except it's at a much, much higher frequency. So we put these sensors on and we can hear the sounds that these damage mechanisms are making. And so what you'll see is a lot of matrix, this is known from many studies and not necessarily with acoustic emission. You'll see a lot of matrix cracking that's active at low stress. So the composite starts to crack through its matrix. You'll see interface debonding and fiber sliding throughout, which are kind of secondary mechanisms. And then you'll see a lot of fiber failure, which is active at high stress. And so that's when you've loaded the composite so much that now the load-bearing structures of the fibers are starting to break. And we're really interested in when fiber failure happens and when it starts to happen in increasing amounts, because it's indicative of when the composite's going to fail. So it's a nice kind of heads up that you're reaching catastrophic concerns. And so when this damage happens, and you can see here these different types of damage. Here's that weak interface. Here's that ceramic fiber. Here's that ceramic matrix. You can have these matrix cracks. They can bond up the interface. You can have fiber sliding, fiber breaking. We basically attach these piezoelectric sensors, and they'll capture the spectra that is results from one damage mechanism. And so the description that's given of AE is, oh, you capture the spectra. It's damage mechanism agnostic right now. We don't know which mechanism is creating this. And we do know that, fiber failure is a big one, reduces component lifetime a lot more than other mechanisms. And so we really want to know which one occurred. And we look to machine learning techniques for this, because in a lot of the literature, people take these acoustic spectra and they reduce it down to a scalar, a few scalars, looking at amplitude, looking at peak to peak. So you're basically, when we looked at this, you're kind of throwing away a lot of information. The spectra is very rich, but you're taking that information and you're just collapsing it down to a lower order, lower rank tensor, which doesn't make a lot of sense. And so we started looking at machine learning techniques in order to kind of look at differences that are really complex and not visible by just looking at one of the scalars of that spectra, but are a result of a lot of interactions in that spectra. And machine learning can pick that up. So this is very quick. We are all familiar with machine learning, but basically the idea is that we have this domain, experimental knowledge, which is this spectra, and we want to learn this function. That's all machine learning is really learning a function. And so that we can map that to the damage mechanism, the image that's happening. The tricky thing with this in experimental mechanics, for example, in acoustic emissions with CMCs, is that this function is dependent on the waveform, but it's also dependent on a lot of hard to capture experimental factors, how well your sensors are coupled, did you pull exactly on axis, and even stochastic factors just in the way the specimens break. So we really do need statistical learning tools here. And so typically in supervised methods, you would compare, you'd build this function F to map from this domain, these acoustic spectra, to the image or the damage mechanism. And then you'd compare the predictions from F with a ground truth, an objective function G. And unfortunately for CMCs, this is not quite possible because G requires really difficult to obtain ground truth data sets. We can use, and we are going to use, I shouldn't say it's not quite possible, we're going to use XCT to start looking at some of these data sets, but there's not a lot of data. These are data sets, these ground truth data sets are expensive to obtain, and at the beginning of this, we did not have them. So taking an unsupervised method in order to make the most use of this tremendous amount of acoustic emission data we're getting where we're very limited in our ground truth data sets. What we did was we basically collect these waveforms, these acoustic emission waveforms, and then we look at the spectra and we extract certain features. And this is what's been done in the literature before, so there's nothing different here. You extract certain features. In the past, these have been like amplitude, rise time, counts, energy, threshold. And then you go ahead and you put them into a feature space. In this case, the feature space is two-dimensional. So the axes can be, whatever you pick as your feature vectors. We, of course, do this in n dimensions, but it's represented here in 2 dimensions because it's on a slide. Then we go ahead and we can pre-process the data in some way, and we can bring it to a space that is like computer derived and is not necessarily as physically based, but is computer derived, and that's a step we can do. And then we go ahead and we cluster. There are many different clustering mechanisms that we can use. We have seen k-means a lot in acoustic emission analysis. I'm going to show that pretty much all the existing literature is using k-means, but k-means doesn't really work because of the assumption that it is a flat Euclidean space. It's a flat Euclidean data geometry, and that is not necessarily true for acoustic emission spectra. And I'll explain what I mean by that. So, okay, I did this. Okay, so we ran experiments to start to get our acoustic emission data. What we did was we actually put 2 specimens at different locations on the 2 specimen models, so 4 sensors total, and coupled them to the sample because if our framework is working well, it should be both sensor independent and location independent. So that lets us probe this. One of the things we found is that with acoustic emission, the path that the acoustic emission signal takes from the damage mechanism, the emitting damage mechanism, to the sensor, if there's too much attenuation, it can really make identifying that signal difficult. And one of the things that can cause a lot of attenuation is the epoxy that couples the sensor to the specimen. So what we actually did was we additively manufactured molds for these epoxy tabs that kept things really, really thin between the specimen and the sensor. And then we tried to impedance match as much as we could with the epoxy choice we had, so that basically we wanted something really thin that the signal could just rip through with no problem and go directly into the sensor. We were trying to keep its path as short and as nice as possible. And these sensors are in different overlapping frequency ranges. And they're up in the kind of the megahertz range, but they're synchronized. So all of the sensors will record when one is triggered, and they'll capture these damage mechanisms. And we did remove some unsuitable waveforms in the experimental configuration. We removed them if there was an out of gauge event. So that would be something that happened in the grips that produced an acoustic emission signal. And we were only looking inside the gauge. That was about 95% of the signals that we removed were out of gauge because that's not where we were looking. We did see, I think it was like 6 events where there were multiple events that happened to overlap. And you can see that quite clearly in the upper right. So we took those out. And then we did see some oversaturation of the sensors. Again, the majority of the signals that we removed, like 95%, were out of gauge signals, but we did see some multiple events, and we did see some oversaturation that we took out. And in the literature in the past, what's been done is, there was kind of a start with this time domain parameter analysis, which was really looking at the time domain, because that's, what the signals in, that's where you're kind of more comfortable with. And so just basically classifying AE signals based on things that you see from the actual spectra. And again, it's kind of scalars, counts, energy, amplitude, duration. So you take these scalars and you kind of classify them somewhat individually. This was the rise time. This is this bin of rise time. This is this bin of rise time. And that wasn't really working very well to understand which damage mechanism was causing things to happen. In the late 1990s, the field really went to frequency domain analysis. and using fast Fourier transforms to calculate the frequency spectra, and then doing the same thing in terms of like, here's a scalar, here's a scalar, here's a scale, but doing it in the frequency domain. And then in the 2000s, it was really kind of a time frequency domain analysis. So looking at especially the Hilbert-Hong transform, wavelet packet transforms, things like that. And so what we did to kind of illustrate the current state of the art is we took 5 basic frameworks that are out in the literature that all take we tried to scope a broad view of what people, what approaches people are taking. Everybody is basically, many people are basically using k-means right now to look at this data. And so we took different frameworks that we kind of named here, and then looked at their encoding schemes and looked at their machine learning algorithm. And then we applied them to our data. So these 5 frameworks are applied to the same data set. And what we were trying to do was benchmark the current state of the art to see if they would give us the same answer, and if they would give us an answer that was consistent with our domain knowledge of what happens inside of composites. These all do use k-means or a derivative of k-means. And so the idea behind k-means is that, you know, you have your input data, you seed it, you have to pick your number of clusters, and you have to pick your representation, which are those axes. So in this case, it's in 2D. You put your data in 2D. So let's say you're looking at medical data. You'd look at the age of a patient, and you might look at the weight of a patient. And you'd put those, you know, here's the age and here's the weight, and you plot your patient data where each point here is a patient. And then let's say you were looking for 3 clusters. So you're looking for has kidney disease, has high potential for kidney disease, and it does not have kidney disease and does not have high potential. And so you'd seed, and these seeds can be random. And what you can do is you can initialize multiple times with random seeds to make sure that you're not falling into a local minima. But you'd seed that data, and then you would calculate the centroids. You'd calculate a distance metric and say, here's my random seeds, coloring the points given a distance metric to those seeds. And then you recalculate your centroid, and then you calculate the distance metric. So some of these change, like down here, it's really obvious. So you calculate your seeds. This one shifts because the center of these shifts it up here, which means these are now closer to this point. And then you recalculate that centroid, et cetera, et cetera, et cetera, until you've clustered. K-means is very, very robust. Clustering is very good at finding complex structure inside of ND data. It's very good at finding that structure. So you can imagine you plot these like data points inside of an ND structure, and it will find like inherent cluster prototypes. You know, these data points all belong to the I probably had kidney cancer prototype. And so that's the general idea. And so we're trying to do this to say, these data points are a fiber break, these are a matrix crack. And so in the literature, far and away, k-means has been used to do this. It is very robust. We do use it a lot. What we'll see is it's not a good choice for this particular application. But to start to get an understanding of what was happening in the field, we took all these frameworks and we applied them to the same data set. And what we found, we looked at 2 different things. We looked at the adjusted RAND index, which is a similarity metric between 2 data clusterings. So I cluster the data using this, and I cluster the data using this, and how similar are they? And then we also looked at, if you look at like, it goes from 0 to 1. 1 is perfect, but over 0.4 in prior studies on in machine learning have been shown to correlate with pretty good performance when the ground truth is known. So the higher the more accurate the performance, the better the clustering. And then we looked at micromechanical expectations. We're very lucky here because in ceramic matrix composites, we have the benefit in this unidirectional composite that we chose of knowing what that damage chronology is going to be. We know that we're going to see matrix cracking early, and we know we're going to see fiber breaks late. And so we very much expect to see that in this simplified geometry, that we see a bunch of matrix cracking, and then we see the fibers start to break. The interfacial phenomenon is more difficult. It can occur in conjunction with both, and we expect that to be somewhere in the middle. So when we apply these frameworks, the first thing we see is that, and so here, each one of these plots is a different sensor. And it's looking at clusters of data. And you would expect this to be sensor independent. So you would expect all of these to look the same at every sensor. It doesn't matter which sensor collected the data, you should get the same answer. And you don't. So each partition is different. And so, and they don't follow the chronology that we expect. So none of these are picking up true damage mechanisms, these low ARI frameworks. If we look at the high ARI frameworks, what we saw here was somewhat similar. So what we did was we took this high ARI framework, the individual ARI, right? And then we looked at the sensors that one framework applied, and we looked at the clustering at the different sensors, which should be the same, that the framework is working. Then we took the different frameworks and we compared their ARIs to see the commonalities in the answers that the frameworks were given. So we looked at the similarities in the answer that the sensors were giving, and we looked at the similarity in the answers that the frameworks were giving. And even though a framework by itself might have a high ARI and might say, hey, I'm totally giving the right answer, all these frameworks are screaming, I'm giving the right answer, and they're all screaming different answers. And that's not possible. And not only are they all screaming different answers, they're screaming answers that they're giving answers that don't match with what we know physically about the micromechanics in these specimens. So the inter-framework ARIs, when we compared the frameworks to each other, was 0, which meant they have completely different, even if they look similar, and this is a good example of like how machine learning can be a little bit tricky. The SOM and the FCM framework to me look really similar, but when you compare them quantitatively and their clustering, they're giving completely different answers. And they're giving completely different answers that in no way match with early matrix cracking and late fiber failure. And so in order to really understand frameworks and accuracy of these ML approaches, if you just look at your framework, independent of sensor model, independent of location, and independent of other frameworks, you might get the wrong idea about how well your framework is performing. And so it's good to take kind of a base data set, apply different frameworks to it, look at sensor models, look at locations, look at inter-framework comparisons. And so these are all giving different answers that don't match with micromechanical considerations. And some of them are really convinced that they're correct if they were just looking at themselves independently. So these don't work. And so there are fundamental changes needed for these acoustic emission machine learning frameworks. Time domain features are not representative. They're largely historical artifact of the literature. And frequency domain is a better representation of the physical basis where the features are coming from. Also, algorithms in the k-means family should be avoided. They only cluster, it's a Euclidean kind of flat geometry for k-means. It's a super robust algorithm, but it doesn't work on certain data types. And this is one of them, because it can only cluster data which is geometrically isotropic. And what I mean by that is if you look on the right-hand side, you can see, we'll look at these two, but let's just look at k-means and spectral, because spectral is what we end up using. K-means is good at clustering like this top for the most part, which is pretty flat. You're looking at Euclidean geometry or moving around those centroids, but look at the spirals. So this is an example of kind of a non-isotropic geometry in 2D. And it's simply, our eyes can tell us where we should partition those, but k-means can't see it because it's only using this Euclidean metric. So it's seeding and then trying to squeeze things in there. So there are different approaches that we can take. And so here, what we're actually going to use is spectral clustering in the frequency domain, which is able to handle non-flat geometries, such as the sort as what we see in acoustic emission. So we're going to go ahead and do that. So what we do is we're basically creating a new framework that's able to handle non-isotropic geometries, and we're going to make sure it's sensor independent, it's location independent, it follows the expected damage chronology. These are all things that should happen if we're actually picking up damage mechanisms. So that's what we're looking for. So we perform this FFT, this fast Fourier transform, we break it, we basically slice it into bins, and we look at the relative energy content that we're in each frequency range. And then we normalize it, because if it's a matrix crack, we're not interested in the loudness of the event. If it's closer, maybe it's louder, we don't care. If it's, we just want it to sound like a matrix crack. And so regardless of how loud it is, we're basically normalizing everything to look at the actual tenor of the sound. And so we basically slice these up, we normalize, and we create a feature vector out of these different energy contents in these slices. And we do use spectral clustering because it is looking at this non-geometric, non-isotropic data. It can also handle uneven cluster sizes. And so that's the approach that we decided to take because it fit our data well. Not all clustering is the same. And so when we did it and we took this approach, frequency domain, normalizing the energy, and then making that into basically a fingerprint and then using spectral clustering on that fingerprint, we were able to create partitions for damage mechanisms in composites. We checked if they were hardware independent. Remember, an ARI over 0.4 is good. So ARI is a little weird in that you think, oh, 0.73 is not that high, but for an ARI, it's very high. So in here, we're looking at different sensors. This is on the bottom. I just pulled a representative example. So you have a sensor here, and then you have the other model sensor here. You see failure that makes sense. This is, we assigned, the spectral clustering doesn't know which mechanism it is. So we assigned that it was a matrix crack and a fiber break based on the damage chronology because that's well established for these composites. So here's our matrix cracking. Here's our fiber failure, and it was sensor independent. Here's the other sensor. Here's our matrix cracking. Here's our fiber failure with a match rate of about 94%. They also were location independent. So then we look at the same sensor, but at different locations. And again, we saw ARI over 0.4, we saw 0.55, and a match rate of about 90%, 88%. And again, with features that made sense. Like this makes sense for a composite, that this would be the way matrix cracking happens, and this would be the way fiber failure happens. The chance that the cluster would fall out this way, be sensor independent, be very cool that would happen if we were not picking up really about the damage mechanism itself. So in summary, we found that these K-means are not useful for damage mechanism. Future sets.
Sam, we lost you for a moment, Sam.
Oh, okay. Am I back?
Just for like 20 seconds.
Oh no. Okay. Is it okay now?
Yeah, it's perfect now.
Okay.
Don't know what happened.
Yeah. So basically, this is very heartening that it's sensor independent, it's location independent, and we're seeing the damage chronology we expect. We did find that K-means based frameworks don't work for damage mechanism identification in this case for these composites. By looking at these frameworks applied to the same data. That's largely because they use non-physical feature sets and don't account for non-flat data geometries. So we made fundamental changes to the way that we capture this feature set and which ML algorithm we apply so that we can look at geometrically anisotropic data. And using that approach, for the first time, we found partitions that do follow the expected damage chronology and that are independent of sensor, model, and location. So this is really exciting because I think it's been a question if we even can identify damage mechanisms in these elastically similar composites. And I think we can. I think we've answered that question. We can identify the damage mechanism. We have found that partial power is a really salient feature. And so our next steps are now to go and further validate this framework using XCT so that we can get some ground truth data as well. And then start to extend this to composites of more complex geometries. We don't know the geometrical dependence of feature vectors. We don't know if partial power is going to remain a salient feature in laminates. And so those are the things that we're going towards, are these ground truth data sets and extending this to full scale composites. That is it. Hopefully I'm not too far off time.
Oh, it's perfect. Thank you very much. Yeah, it's great talk. It's very, very interesting. I remember you telling me a little bit about this when we were starting on this topic. Was a discussion at the Starbucks, I think in San Diego, and I think you've come quite far now. Maybe I'll start with a few questions. I was about to suggest doing some CT to get some ground truth, but I get that you have that covered. I was so a similar question is: do people? I'm not very familiar with AE measurements, but do people have done very specific, very maybe unidimensional or one fiber experiments to try to calibrate the frequency data you can get from a single event? Do people do this?
No, I think partly because of the there's been a little work, but it changes so much in the entire composite. So when you like single fiber, you know, testing or the break signal of a single fiber being tested is very different because the experimental constraints have such an effect on it than it will behave in an entire laid up composite, because the processing of those is also different. So the way that a fiber is processed as part of a kind of put into a composite with the weak fiber matrix interface, and the way that the signal behaves there is very different. So it's
right. So it would be better to do some kind of CT measurements to get some ground truth data based on a real specimen. Okay. So I have maybe a naive question, but could you explain again what was the
as well?
Sorry. Could you explain again why the I guess that was this SOM and the FCM k-means based models? You said they were not working, although they look like they were doing a good job, but it didn't in the end. Could you try to explain that again?
Yes, there were three things we were.
Connection is really bad.
Sorry about that. I think that might have been my end. So the when we were looking at the different frameworks here, the different frameworks, we're looking for three things. We were looking for were they sensor independent? Were they location independent? And when applied to the same data set, did all the frameworks give the same answer? And none of those things were true.
Okay.
Oh, and do they follow the expected damage chronology? So we're actually looking for four things. We took these frameworks and we applied them to our data, to look at, are they location independent? Are they sensor independent? Do they all give the same answer? And do they follow the expected damage chronology? And these frameworks didn't do any of those.
Right. Okay. And then moving to the frequency space of the feature based on the frequency, then solve the problem. Okay. Great. Thank you.
Right. So when we went to our new approach, we saw those satisfied.
Right. Do we have any question from the audience? Yes, Daya, can you come here? Yeah.
So, hello. Thank you for the presentation. So, according to these four criteria that you just mentioned, is it possible to say that at least in the frequency domain, the signatures that that allows to distinguish the difference in terms of mechanism are not specimen dependent? It means that it would allow you to do some prior prediction for a new specimen?
So this is a really good question. And this is at the heart of, this is right at the heart of it, is we took the frameworks and looked at their operability applied to a single specimen, right? So we were just answering the question, like, do these frameworks find what they think they're finding? And is this even possible in a single specimen to distinguish the damage mechanisms, which we answered is yes. But your question is really the crux of the next thing we're going after, which is, can you generalize these frameworks so that you can basically give it a composite? Is the framework like tied to that specimen, right? Or can you and you have to always have domain knowledge to answer, you know, we had a really easy specimen. So we could say this was fiber breaks and matrix cracks. That is the next question is, okay, so we can do it, we can identify it, but can you take a more complex geometry and do you have to like revalidate and figure out the framework for that? Or can you create a framework that you can extend to different composite geometries, which would be a lot more useful? Yeah. So we don't know. We're looking into that now. That's the next step.
Okay, thank you.
Any other question? Okay, Sam, that's it. Thank you very much. And this is the end of the
All right, thank you
BIGMECA
very much
seminar.
for
Thank you for all the speakers. I guess we will talk more about this when you're in Paris soon.
I'm really looking forward to it. Thank you.